Our next presentation in the water stream is why are actuators important and are they making your life easier? This presentation will be by Juan Tan. Juan has a degree in mechanical engineering from the Imperial College in London. Juan started at Spartan Controls in 2011 as an application engineer and is currently a technical specialist of valve and actuation focused on the municipal industry. He specialized in valves and actuation and worked on several Metro Vancouver and local municipal projects. So please welcome Juan. Too many things here.
Excellent. Well, thank you for having me here. It's great to actually speak to people. It's a great experience, a slight social interaction. So thank you for having me here. All right, so today we're going to talk about actuators and how they're making your life easier. It's going to be kind of an overview of actuators. So for those of you who have seen them out in your plants or out in your distribution, you probably know that actuators are out there, but you haven't really thought about them more than they're there and they work. So we're going to do an overview, a bit of a fundamentals, talk about the considerations when I'm specifying an actuator for some of my clients, what's going through my head, what's the thought process there. Then we'll look at different types of actuation, different types of designs, and why I would consider one versus the other. Then we're going to go into electrification, electric actuators, the smarts in terms of those electric actuators and how those smarts and the new advances in technology and actuation can actually help you out and help your plants get more smart and get access to more data. All right, so let's kick this off. So what is an actuator? Now, actuators come in all different shapes and sizes. You see some pictures there. You can see there on the right, you've got a huge pneumatic. Oh, sorry, is that right or left? That's left. On the left there, you can see a large pneumatic orange actuator, and they come in all sizes. That one's larger than a person there. It's connected to a ball valve. And then there on the right, you can see that electric actuator connected to a huge butterfly valve. That one is several meters long, and that butterfly valve now resides in New Orleans. It was actually installed back when Hurricane Katrina hit that area, and there was mass flooding, and now if the levees were to break, these valves would open, and they're able to drain an Olympic-sized swimming pool in seconds. So actuators are what help move these valves. So they're the things that provide the motive force for our valves. Now, when we're looking at actuators, because there's so many out there, it becomes very difficult. There's a lot of questions that get asked. I like to make things a bit more simple. So there's three basic questions that would be asked. Firstly, what type of valve are you mounting it to? That's the first question you should ask yourself. So if you're looking for an actuator, you likely have a valve around. So what valve are you looking at? There's a lot of valves out there as well, and it's my job as to be a valve and actuator specialist, so I spend a lot of time talking about different valves. But when you're talking about actuation, it's easy to just split valves into two categories. Is it a linear type valve, or is it a rotary? So does it go up and down, or does it turn? So once you've split it into those two, you've helped to kind of define which design you're going to go for. Actuators that are linear can't be used on rotary and vice versa. And then the next thing is my valve manufactured to be mounted? Can I mount an actuator easily to this? So a lot of the times when we look at valves and we haven't thought about it well, we get something like this. In my office, we call this a Christmas tree because it's where someone purchased a valve. They didn't think about what actuator they were going to put in it. They didn't think about the functionalities. They didn't ask themselves these three questions. They stuck something on it, then they stuck something else. They stuck something else, just like a Christmas tree. So that's what we have there. That's not ideal for anyone, and especially your operators, or I'm sure your operators have seen something like that, and they're just like, how do I even repair this? Like, where do I start with my PM? Other things that we're looking at is the mounting pad. A lot of these valves, when they're purchased, they haven't been manufactured with actuation in mind. This is a ball valve on the left there, which it doesn't have a mounting pad with a sufficient mounting pad for the weight of that gearbox. So we had to custom fabricate a additional mount that kind of bolted into the side to give a bit more structural integrity to that mounting pad. And then on the right, that was an old wedge gate, and that wedge gate didn't have a mounting pad at all. It was a manual gate, and then the customer came to us and said, hey, we want to electrically automate that. And so we had to weld a pad onto that. Here, there's absolutely nothing except a stump in the ground, but this connects to a valve at the very bottom. You can see on the right there that there's a butterfly valve connected to this. And so we had to custom fabricate some sort of foundation to be able to mount that actuation. And here's just a custom retrofit that we did. This is one of our Metrovan sites that we did a custom retrofit while the valve was in line. So that's another issue. Can we take that valve out of line to do a custom mounting kit? Like, will we have to have downtime in order to do a custom actuation job? And in this case, it was an issue, so we had to do this actuation in line. So how easy is it for us to actuate or put an actuator on that valve? So once we've thought about that, we know what valve we have, we know whether this valve is good to be actuated, we know whether we can take it out of line. Then let's talk about what we want the actuator to do. So we look at we look at what we want it to do, and we split it into a few categories. And I've got a few categories here just to make it a bit simpler. So are we trying to control or isolate? So those two things are pretty easy to understand. Do you want it to open and close, so fully open and then fully close? Or do you want it to be able to modulate? Like, does this valve have to be 50% open? Does it have to control pressure? Does it have to be in a mid-travel point? And if the answer is yes, then you have a control actuator. If the answer is no, I just want open and closed, then you have an isolation actuator. Pretty easy to understand. Now, fail action is extremely important when it comes to actuation because it's a safety concern for a lot of the processes out there. So by fail action, I mean if there was a failure to the power supply, so the power that you're supplying to that actuator, if that was to fail, does this valve need to go to a fail position? Does it need to fully open or fully close? A lot of the times when you have emergency shutdown valves, you'll find that these valves will need to fully close in order to protect the rest of your system downstream. Is that the case for this valve? Or some, especially with drain valves, would have to fully open in order to dump a line if you were to lose power to part of your system. So what fail action do I need? And in order to get a fail action, it often really impacts the design of the valve. And the last thing is stroke speed, and it's pretty self-explanatory, but it is a big consideration, especially on the water side. If you've got a valve that's stroking extremely fast, you get water hammer. It's not ideal. So what is the speed that you have to open and close this valve? And a lot of the times it doesn't matter, but when it does, we need to know, and you guys need to know as well. So that's another consideration there. Now, just to go back over fail action and to have some graphics there to kind of understand that, what we have here is we have a gate valve and we have a linear piston actuator. And when we ask for no fail action, usually you have an actuator like this. So in this case, you've got air going to the bottom of the piston. It moves the valve up. Then you have air going to the top of the piston and the air being vented from the bottom and moves the valve down and closes the valve. Now, if you were to lose air pressure to this valve will just stay in that position. Obviously, if you were to lose pressure totally and you were in the open position, you might actually find that the gate will pull that piston down. So we generally call this type of actuator a fail indeterminate actuator. It means that when you lose power, you don't really know where exactly it is. So there's no fail action for this kind of actuator. It's generally the most economical type of actuators that you can get out there without fail action. Now, if you do want a fail action, we have to have some sort of stored energy. So in order to move it to that position when we lose power, generally you'll see something like a spring. So in this case, we see a spring. So here we've powered the actuator opens, compresses that spring, and then once we lose power, that spring takes over and it closes your actuator. So an emergency shutdown valve or a valve that needs to be fail closed would look much like this. There are other forms of fail action. So you can see there's like the accumulator, volume tank, UPS, battery backup, and super caps as well. Generally, if you're doing an emergency shutdown valve or if you want something that is reliable and if you want it to be guaranteed to shut off, I would go with a mechanical fail action, and that is with a spring fail action. It's the most reliable out there. But if you can't have a spring fail action, there are other forms out there. Okay, so we've answered the first two questions. We've looked at what valve we're mounting it to. We've looked at what we want the actuator to do, what kind of functionality. There's a few other functionalities out there that I'm not going to go into because they're more niche. If you do have other things that you want to know, that you're curious about, feel free to ask me in the questions section. Or I'll have my contact details. Feel free to shoot me an email or give me a call. I love geeking out about this stuff. The last thing is, what are the constraints of my actuator? So what is my motive force? What kind of energy do I have to move this actuator? So do I have air? Do I have hydraulic power? Do I have electricity? Or do I have power gas? Or do I have the power from my line? Like, am I actually powering it using the water pressure from my line? The other thing is size and weight. Obviously, we saw before that actuator was extremely large, couldn't fit on that ball valve. This is another thing. If we've got a large actuator, is it going to be an issue with the piping system? Is it going to be an issue with the size and weight? Cost is obviously an issue. If we're looking for all this functionality, but we don't have the budget to fit it, it's obviously an issue. And the last thing there is environmental. So especially on the water side, if we've got a hydraulic actuator and there's a probability that there can be hydraulic fluid leaking into our process, that's an environmental issue. We don't want that. We don't want to pollute our water. Also, if we're using the water to power our actuators and we're draining that water, that could also be an environmental issue. It's also an issue with process gas. If we have a gas line close by and we're using process gas, not sure why we'd be doing that on the water side, but on the wastewater side, we could be doing something like that. And we're venting, that's greenhouse gases. So the environmental issues are a big thing for us at Spartan, and we're always looking to decrease your footprint. So with these constraints in mind, actually you can see a little picture there. It's a little picture of a solar panel. It's a neat little, bit of a niche application, but a neat little thing that we have for some of these actuators that out in the boonies, absolutely no power can get to it. It's just a nice little picture here of what we mean by space constraints. Oftentimes we all have these good ideas, and then when the poor installation guy or operator goes to work on it, he's like, hey, I can't even access this valve. I can't even see this or this actuator because it's so cramped. And in this case, we had real issues with how to fit this actuator, and we had to orient it in this exact orientation in order to get that actuator in. Okay, so now we've asked the three questions of how to specify our actuator. Now let's actually talk about different types of actuators, what's out there in the market for you. So let's first talk about pressure-loaded actuators. Like we were showing you before with actuators, pressure-loaded actuators are actuators that use pressure in order to move, just like that cylinder before. So the most common that you'll probably see at your wastewater treatment plants and your water treatment plants and even in distribution is the rack and pinion actuator. It's a pretty simple concept. You have two racks on either side. They're connected by these gear tooths to a pinion. When the pressure pushes in on either of those racks, they rotate the pinion and they give you your rotary action. So this is only for rotary valves. You can see there on the top, we have a double acting because there is no spring to push back. But we can see at the bottom there, we can also install a spring pack in order to get our fail open or fail closed. It's generally the most economical type of rotary pneumatic actuator out there. It's good for medium cycles. If you're cycling constantly with your process, I probably wouldn't recommend it. But if you're cycling, 5 times a day or so, it's not a bad actuator to have. I have seen these used on hydraulic. I do not generally recommend it. That's why I've put here typically pneumatic only. There are a few configurations out there that can be used on hydraulic or on water. They're generally not as reliable just due to the pressure ratings and due to the design. So rack and pinions are generally used for those smaller type rotary, like those ball valves or those butterfly valves ball valves up to 6 inch, I'd say, and butterfly valves up to maybe 12 inch. As soon as we get up to these larger type actuators or larger type valves, we need to use something that can provide more torque. And that's where we move into the Scotch yoked actuators. So there's an increased start and end torque with these, which help us kind of break the valve out of the sticky seats. It's more of a robust design. We don't have those gear tooths anymore. We have kind of that lever and yoke design, hence it's been Scotch yoke. So these are used for way larger valves. So the initial large actuator that we saw, that's a Scotch yoke design. Just got a few pictures here. You can see there that there's a flatbed truck there, and there's a really huge Scotch yoke actuator on that. So these things can get extremely big. You can see there that these things come generally with a spring canister for that fail action, and the sky's the limit. They're also quite modular, so you can often get different types of functionality. You can see there's hand wheels and things that can be installed onto those as well. So pretty scalable, pretty modular, come with a lot of different functionalities. A lot of the time when you don't have pneumatic or hydraulic power to power this type of actuator, you can also use them on water. So here's an example of us using a Scotch yoke actuator using city water. So the city water goes in when they want to close this valve. The valve vents, and the city water's drained to a drain there. So that's another way of doing it. Now I've talked about kind of the most common pneumatic actuators. There's also hydraulic actuators out there. The reason why you would move from a pneumatic to a hydraulic is either because, firstly, you don't have pneumatic power and you do have hydraulic power, and secondly, because you have such a large valve that you need more pressure in your actuator in order to stroke that valve. So for hydraulic actuators, you can get a lot more pressure because you're generally pressuring hydraulic actuators to around 3,000 psi. So you can have a smaller bore and you can fit that actuator into a smaller space. Generally with pneumatic actuators, they're pressured up to a maximum of around 120 psi. So in order to get the same amount of torque or same amount of thrust, you need a much larger bore there. Generally, hydraulic actuators are self-lubricating, so they are more reliable, but then you do have to take care of your HPU, your hydraulic power unit, which can be more maintenance and generally more cost to have an HPU. Here's just a neat little solution if you need a safety valve in the middle of nowhere, and you don't really want to look after this valve. You only need this valve to close if, say, there was a line leak or there was say there was an ozone leak or something like that, and you needed this part of the plant to shut down. Basically, the best pressure guard here, it's kind of a standalone unit. You pump it up using that lever and that hand jack, It's got hydraulic fluid in it. You open it up using that hand jack, and then if you ever get a trip to your system, you can just trip that little switch there, and it will shut for you. It's just a little schematic to show how it works. And then your system will shut down. It's a nice little safety valve actuator assembly that you can use in order to protect your system if you don't have any power or anything around the place that you want to isolate. Okay, so we've talked about pressure-loaded actuators. We've talked about a few different, the most common ones that are out in industry. If you guys have any questions about other types of functionality that I haven't talked about, other types of actuators that are less common, feel free to just fire me a question there. So let's get into electric actuators. So you guys will probably see a lot of electric actuators around your plants, and that's because generally you don't always have pneumatic power, you don't always have hydraulic power in all locations. So most plants will have some form of electric actuation, especially on your like outfall types or your intake gates. Those are usually kind of remote areas where you don't have any of these power sources. You can just run wiring and run electricity out to these places. So electric actuators come in all different shapes and sizes. We can do them for extremely small torques or thrusts up to extremely high torques or thrusts. So you can see there, there's a large size range. We can do electric actuators in both rotary and linear, but we need to know beforehand because they're not easily interchangeable. We're able to do them for all different types of power supplies, but not all of them are able to take all power supplies. So it's good to know what power you have on hand before going out to expanding a part of your plants. Also, with electric actuators, you're able to do things like use that fail-safe battery, your UPS. But like I mentioned before, the most reliable form of fail action is always the mechanical spring. Generally, it's a lower installation cost. You don't need to have an HPU. You don't need to have a compressor around. So not too much of an issue. You just need to have the electric actuator itself. The last two things there are probably one of big other reasons that you wouldn't think of, but electric actuators are generally quite a bit smaller. We saw on one of the first few slides, there was that huge butterfly valve, and the actuator was actually quite small in comparison with the butterfly valve, and that was an electric actuator because we're able to get real mechanical advantage by installing gearboxes and things like that onto electric actuation in order to get the torque that we require. And the last thing which I'll be talking about is with electric actuators, we're able to go digital or go put smart diagnostics on electric actuators. So we're able to get diagnostic information back from them. So here's just a slide to show the different types of actuators out there. You can see on the top left, there's some linear actuators. So those linear actuators obviously won't be able to be used on a rotary. And then you have the kind of middle right there, those are rotary actuators. And then on the right there, those would be our larger type actuators for those large type gate valves or large type butterfly valves. So there's a load of different designs out there. Each one is designed for that particular size range and that particular functionality. So just because you've got a few actuators that work well for a certain application doesn't mean it's going to work well for all applications. So it's good to understand the range of actuators that are available to you, or else you might be paying a lot more for an actuator that you didn't need to pay more for, or you might actually be putting a less robust actuator on something that really requires quite a robust actuator, and you won't be able to get the lifespan that you expect out of it. So it's always good to know the options that you have out there. So just going over what the general parts of an electric actuator. So an electric actuator will always have a motor. So you can see there an electric motor. It's connected to motor gears. That's to give you the mechanical advantage to get that torque. Oftentimes, those mechanical gearing will be connected to a worm gear or spur gears that are connected to some sort of drive nut or stem nut, which is connected to your valve. with electric actuators, as opposed to pressure-loaded actuators, you're not so, you wouldn't know when this valve has opened or closed unless you have some sort of position sensing. So with electric actuators, you'll need to have a position sensor. So either a limit switch or something to let the actuator know I've fully opened, I've fully closed, so that you can cut power to your motor. And also for electric actuators, torque sensing can be very extremely important, especially for those larger type valves, so you don't over torque your valve and you don't damage your valve there. Not all electric actuators come with a hand wheel or manual override, so that's something that you need to be sure to specify if you need. So that's just a general overview of electric actuators. Again, you need to understand whether it's rotary or linear. That's extremely important because generally your drive nuts or your stem nut is going to be machined for your valve, as well as your mounting, as well as all your custom parts there. So you can see here that we have a linear type actuator. The linear type actuator will have a stem that kind of rides through it. It will have a threaded stem. That threaded stem will ride up through the stem nut and come up through the actuator. And that's why we've got these little stem covers, stem tubes, generally best practice. And so you guys have probably seen actuators like this on gates and things like that. Now, it's important to understand the gear train, the mechanics or the mechanical components of your electric actuator. Generally, you want to have a worm gear train, and that's because it's an inefficient gearing. It can't be back driven. So if the actuator can't be back driven when you lose power, this actuator will just stay in that same position. So it'll be truly fail last. For the smaller sizes, generally you see spur gears, and spur gears can be back driven. So they won't be truly fail last. You might not know where your valve is. Generally, spur gears are found on smaller type valves, like you can see there. There's like a 2-inch ball valve. It's generally not so much of an issue. But if you do need your valve to truly fail last, you want to have a worm gear there. There's some other types of gear trains. So there's rack and pinion, like we talked about before. There's linear ball and screw. And there's planetary gears. This is one of our more advanced actuators, which actually incorporates all three of those mechanical gearing types in order to be able to give you a spring open and spring close, which we'll talk a little bit about later. Okay, with electric actuators, generally you'll see them connected to auxiliary gears as well, and that's just so we can multiply that amount of torque. And you can see here we're able to put them on extremely large valves because of the gearing there. Okay, I'm going to touch quickly on fail-safe electrics. So fail-safe electrics are extremely difficult to come by. It's not as simple as the pressure-loaded side. It's not so easy to just put a spring canister on that. So generally with fail-safe electrics, we'll need to use a spring case, but we'll generally connect that to the stem of the actuator. So that's what you can see here in the slide. But generally, when you get to the larger sizes, it's a lot more difficult to fail open or fail close. So we use something like a Belleville spring pack design, which is what you can see there. We're able to do that with rotary and linear as well, so there are options for fail-safe electric. And once you get to the really large sizes, we generally put our hydraulic and electric together. So what we have here, before we'd usually have an HPU connected to a hydraulic actuator. Then a lot of the people in industry thought, why don't we just integrate those two, and why don't we just bolt on that HPU to the actuator? Nowadays, we have an integrated type of actuator, which we generally call the electro-hydraulic, where you have an HPU pretty much bolted on to your electric actuator, your hydraulic actuator. So it's an electric actuator, but it doesn't require any hydraulic power. Now going into the control part of electric actuators. This is kind of the fun part of why electric actuators are kind of moving us into the 21st century. So with electric actuators, there's two different types of control. There's electromechanical and digital. In olden times, they used to be mostly electromechanical. Those are printed wiring boards, and those are very reliable, very easy to troubleshoot. Generally modular look a bit like this. Now, these are really common in industry. They're really common when the operator doesn't need to interface with this actuator very often because they're the most reliable sort of actuators out there. So we still see a lot of these in industry for the reasons stated here. They're modular, they're easy to troubleshoot. You can go there with a multimeter and figure out what's wrong with these. Here's just our M2CP. You can see the modular design there. Pretty simple. You can use it with all different types of current supplies. A lot of these ones were installed 40 odd years ago, and you've probably seen some in industry. These are all old Brews actuators. These actuators have often outlived the documentation that went with them. So these do last an extremely long time. So now a lot of our actuation has been moved over to digital because we're now in a digital age. A lot of our plants are trying to get data. We're trying to understand where our processes are currently at. So the benefits of digital is instead of us having to commission these using screwdrivers or mechanical components, these things can all be done via software. They can all be done digitally. And digital, being able to do that digitally means that it's also non-intrusive. So if we're in a wastewater treatment plant or we have a gas line close by, we don't need to have an intrusive commissioning, or we don't need to have a hot working permit. Also, with digital, we're also able to get snazzy LCD displays, which helps our operators out. Our operators can walk past an actuator and get all the information that they need without having to kind of go into the nuts and the bolts of those things. They're also able to see alarms, so if something's wrong, they can look in that LCD display, or they can also look at their PLC or the DCS, and that they can get all those alarms quite easily there. This is our Bettis XTE. It's our kind of our golden standard for smart actuation. It comes with all the diagnostics and all those capabilities that I'm talking about in this presentation. Comes with all those snazzy little commissioning capabilities and also the LCD screens. Other cool things is we're all going wireless. We're all constantly on our phones. So these also come with wireless capabilities, wireless HART capabilities or Bluetooth capabilities. So a lot of operators have actuators that are not accessible, or you need a confined space in order to get there to access these actuators. With new Bluetooth capabilities, you can take your laptops or devices out there, and you can get the commissioning data right to your devices. Or if you don't even want to go out to the field, you can go to your DCS and you're able to get all that commissioning data. You're able to get those alarms, alerts very easily to your DCS without even having to go out to the field. So in an age where everything is connected now, we're moving more towards a wireless or a very connected plant. So that's what's been shown here. And the last thing in terms of smart capabilities is the ability to be able to take those configurations and copy them easily, monitor without having to get your operators to run out there constantly, and to diagnose problems without having to spend hours on the phone. So in terms of that configuration capability, what we're able to do is we're able to save the configuration of an actuator onto our software. You can see here, this is our DCM Link software. Everything would be downloaded onto that software. So if you had a spare in stores and you needed to replace that actuator, you could just upload that configuration extremely quickly. So you can see here, there's quite a lot of things that you would maybe want to configure. But now at a push of a button, you can configure that new actuator, install it, and you're done. If you want all your actuators to have the same configuration, you can just copy and paste to all your actuators, and you're pretty much sorted. It's a lot easier. Whoever's setting up your actuators doesn't need to go in there with a screwdriver and get that all done. And all that is saved to a local file. So if you had forgotten, or your old instrument tech has now retired and all that information had left with him, but you still have those save files. So you're still good, still able to configure your actuators to the plant standard. Now, the second thing is you're able to monitor. So in terms of those alarms, those all come back through a dashboard. even if you don't really understand too much about these actuators, green means good, red means bad. Pretty easy to understand. And when those red alarms come up, you can know that something bad has happened, and now you need to look into this a bit further. You can see at the bottom there, we're able to do torque trending, and so we're able to actually do the diagnosis in the software itself. So the software can give you troubleshooting tips and information that you can call someone like myself, and we can help you with that troubleshooting extremely rapidly because the software has already done most of the troubleshooting for us. These are a few little indicators and a few little alarms that are easy to kind of just be picked out from the interface. And just going over just having a bigger diagram here of the diagnostics. That's a bit of the diagnostics there. So a lot of smart capabilities through these actuators. And the reason why we want to have the ability to diagnose and the ability to catch these alerts and alarms faster is because of the savings we're able to get from that. Oh, just a lot of animations here. So if we're able to catch these beforehand, and the alert isn't just the failure of the actuator, we're actually able to decrease the costs and decrease the amount of labor that goes into repairing your actuation and repairing your instruments out there in your field. So you can see here that if we have some way of diagnosing, like smart actuation, smart instrumentation, we're able to get an instrument alert, and your instrument tech or your maintenance group will know of that failure before it actually happens. And here we can tell that if we're able to predict that maintenance cycle, we're able to greatly decrease the costs, not just to do with parts and not just to do with failure and damage to equipment, but also downtime and also operations costs and labor as well. So this is just a little chart to show that there. So in a nutshell, we've gone over what an actuator is. We've gone over the questions of how you would look through the considerations and evaluate what actuator you need. We've looked over different designs of actuators out there and what's available on the market. And then we've looked at the new technologies, the new smart technologies that electric actuators offer in order to allow you to be connected and allow you to catch and diagnose issues beforehand and save costs to operations and maintenance. Okay, perfect. If you guys have any questions, yeah, far away.
Juan, that was a great presentation. Thank you for that. It doesn't look like we have any questions from the audience right now, but I have a question for you.
Yeah.
So let's say a utility, a water treatment plant or even a wastewater treatment plant had an actuator in place that was installed or is not functioning correctly. Do you or Spartan provide services for technical support on that?
Yep, for sure. We have two types of services that we can provide. So the first service would be if you're troubleshooting some of our products or some of our actuators out in the field, you could call someone like myself. My number's there. I can troubleshoot over the phone, or if it is a larger issue, I could actually go out there and help you troubleshoot out in the field. And we also have technicians. So we have factory certified technicians that can actually do the configurations for you. So say you didn't have instrument techs to do the troubleshooting or to do the installation and calibration, we can fly them out and they could do that for you. So those are the two services that we'd provide for something like that.
Thank you. We have one question come in here. It says, what types of speed would those valves close at?
Sky's the limit. It really depends on your application, right? So if you had, let's say let's say an intake type butterfly valve that was, I'm going to throw out a number, 48 inches. Generally you want that actuator to actually close quite slowly because you don't want to shock the system. You don't want water hammer. So if it's a butterfly valve, I'd say 5 seconds for every inch of 5 seconds for every inch of diameter of that valve. So with 48 inches, I can't do math right now, so 48 times 5.
Thank you very much. On behalf of the EOCP, we really appreciated your presentation today, and thank you for coming in and providing all this information to us.
Yeah, not a problem. Thanks for having me.
So with that, that closes out this session on the water stream. We're going to take a 15-minute break, coffee break. So please take this time to stretch your legs, get some coffee, and we'll see everybody back at 3 o'clock for the next session. Thank you.